Swayam Prabha. Digital India. Educated India.
In the last class, I have discussed that how we can determine the deformation of lateral loaded pile by for single pile, as well as I have given the concept that how we can determine it for the group by using elastic analysis. And for the bearing capacity or the load carrying capacity of the pile I have already discussed for single, as well as the group is the same as we did it for the single. So, now this class I will discuss how we can I will give a solution for the general solution for P y curve. Now, for P is basically stress, Y is the deformation. So, it is stress versus deformation curves for the lateral loaded pile. So, now in this case we are assuming that pile is modeled as beam and which is resting or attached with the spring. Okay. Okay, which is attached with the spring, and we are applying say horizontal load moment at the head of the pile or top of the pile. Suppose this is your y axis and this is the z axis, and this is the value of kh. Okay. Now, if under this condition, that is subjected to only horizontal load and the moment, and then under this condition the general solution of the beam equation will be. So, that means we are applying this solution will be E p I p d to the power 4 to the y for y z to the power 4 plus k h d y, that is equal to 0. Okay. So, this is your generalized solution for the beam subjected to H and the moment, but here why it is 0? Because there is no UDL is acting. Okay. So, it is only horizontal load and the moment is acting. So, that will be taken care during the application of the boundary condition. Okay, so, this is the common beam equation that I have already discussed, all I have derived even. So, how this equation is coming during my shallow foundation class on beams on elastic foundation. So, you can see those lectures and then you will find that how these equations is coming. And this equation only difference is that in that case it was only E I and here it is E p I p, that means elastic modulus of the pile and moment of inertia of the pile. In that shallow foundation case we used k h into b, sorry k into b. B is the width of the foundation and k is the subgrade modulus width of the beam, but here we are using k h into d. D is the diameter of the pile, or if it is a square pile it will be width of the pile. So, this is the equation if no this is the condition that the beam with the spring. Now, if we can go for this is our case 1, we can go another condition. Suppose this is your beam which is again attached with spring Okay. But here it is subjected to H moment plus a compressive load P z. Why this compressive load? Because when the pile will be subjected to lateral load, definitely at the same time pile will be subjected to compressive load, because of the load which is coming from the superstructure or the so that means pile will not only be subjected to horizontal load, at the same time pile will be subjected to compressive load also. So, in the first case we have not considered the effect of that compressive load. In the second case, we have considered the effect of that compressive load. So, the basic equation will slightly change. So, this will be the basic equation plus P z d square y d z square plus k h d y, this is equal to 0. So, this P z is the compressive load, which is acting on the pile along with the lateral load or the horizontal load H. So, this is the second one is more generalized equation, because in that case the effect of compressive load is also included, and if you put minus P z, it will be tension under uplift. Okay, but here it is under compression you are talking about. So, now how we will solve this equation? How I solve this equation? So, for the solution purpose, so we have to again we will solve this equation by finite difference technique. Now, when we are talking about these finite difference technique, so we have to divide this pile into number of node points. So, suppose this is the pile and we have to apply the number of node points. Okay. So, this is the number of node points. So, for this is node number 1, 2, 3, similarly this is n minus 1. So, we have divided it number of node points with this distance between the node is del z. Okay, this we did it for the beams on elastic foundation concept case also. But here how many boundary conditions are required? So, we need 4 boundary conditions. Okay, so, and there if I express this equation in finite difference form, so these equations will be I can express this equation 2. So, equation 2 in FDM in finite difference method, if I want to express, that will be E p I p divided by del z to the power 4, then y I plus 2 minus 4 y I plus 1 plus 6 y I minus 4 y I minus 1 plus y I plus 2 I minus 2. So, I have already discussed how these equations are coming in finite difference form. Then plus P z divided by del z square, this will be y I plus 1 minus 2 y I plus y I minus 1, then plus k h d y I, that is equal to 0. So, this is the finite difference form of equation number 2, because that is the more generalized equation, because where we have considered the effect of compressive load also. So, now these equation we have to apply on all the nodes. So, that means, here you can see there is a term I plus 2, there is a term I minus 2 also, this is I minus 2, there is a term I minus 2 also. Okay, so, there is a time I minus 2. So, that means, if it is I minus 2, then if I will apply this equation as node number 1. So, then there will be I minus 2. So, that means 2 imaginary nodes will be required if I want to use this equation at node number 1. If I want to use this equation at node number 2, one imaginary node will be required. Similarly, for n, if I want to apply this equation at n at node number n, then there will be 2 imaginary nodes will be required. So, n plus 1 and n plus 2, and for n minus 1 node, there will be 1 imaginary node will be required. So, that means 2 plus 2, 4 imaginary nodes will be required, 2 in the in each side. So, that means we have to apply 2 imaginary nodes we have to consider. So, this is 1 and this is 1. So, this is 2 dash and this is 1 dash. So, now for point node number 3 to n minus 2, you can apply these equations, no issue, no imaginary nodes will be required. But so that means here also there will be n plus 1 dash, then another equation n plus 2 dash. So, this 1 dash 2 dash or n plus 1 dash n plus 2 dash, these are the imaginary nodes. Okay. So, and you know that these nodes, because these are not the real nodes, they are the imaginary nodes. The deflection of these nodes, we have to convert it to the deflection of the real nodes, and that you have to do by using the boundary conditions. Now, what is those boundary conditions? So, that means here how many boundary conditions will be required? This is 1, 2, 3, 4, 4 boundary conditions will be required. So, for the boundary conditions, okay, first we will go for the free headed pile, then we will go for the fixed headed pile. So, for the free headed pile, that your at the tip of the pile, that means at the base of the pile, shear force will be equal to 0 and moment will be equal to 0, because the tip is considered as a free end, because it is at the within the soil and it will be considered as a free end. So, we can take this is the slope will be 0, moment will be 0. So, that is the condition for free end. So, that means for free headed pile, both the ends will be treated as a free end, and for the fixed headed pile, the top end will be treated as a fixed and the bottom end will be treated as a free end. So, if it is shear force and bending moment is 0, so I can write that if Q is equal to 0 and M is equal to 0. So, for the moment part or the shear force, I can write that this is E p I p d 3 y d z 3 plus p z d y d z, that will be 0 at z is equal to L. Z equal to L, L is the length of the pile. Okay, Z is the length of the pile. Similarly, for moment is equal to 0, I can write that E p I p d square y d z square will be 0 at z equal to L. Okay. Now, at the free end of the pile, so here the shear force will not be equal to 0, because the shear force there is a horizontal force is acting, because as I mentioned we have incorporated the compressive load effect in the equation. but we have not incorporated the H and M effect in the equation anywhere. So, that H and M will be incorporated through the boundary condition. So, for the free end of the pile, your this shear force E p I p d 3 y d z 3 plus p z d y d z, that will be equal to H. That will not be equal to 0, because now a horizontal force is acting. So, that is at z equal to 0. Similarly, for the bending moment, E p I p d square y d z square, that will not be equal to 0, that will be equal to m 0 at z equal to 0. So, this is the free end pile. So, this is the free headed pile. Now, for the fixed headed pile, your the shear force for the fixed headed pile, that shear force equation will be same as this equation E p I p d 3 y d z 3 plus p z d y d z, that will be equal to H at z equal to 0. Okay? But dy dz will be 0 at z equal to 0, because in fixed headed pile moment will not be 0. Shear force will be that shear force that is developed, but moment will not be 0, because for the free headed pile we put moment is also applied some moment, but here the condition is that for the fixed headed pile, one is the shear force equation that I have written, another is due to the slope at that z equal to 0 will be 0. So, this is from the slope consideration, this is shear force consideration. So, this is shear force consideration, this is the bending moment consideration, this is shear force, this is moment. Okay, this is the at z equal to 0, and for at the tip of the pile, the boundary condition will be same as the free headed pile. So, that means at the tip of the pile, this will be E p I p d 3 y d x 3 d z 3 plus p z d y d z, that will be 0 at z equal to L, that is shear force consideration, and E p I p d square y d z square will be 0 at z equal to L, that is bending moments consideration. Okay. So, you can use these 4 boundary conditions for free headed pile and the fixed headed pile, and then you can solve this equation and you will get the deformation, or once you get the deformation, then you will get the bending moment, slope, shear force, whatever you want. But the one thing I want to mention, that what would be the suppose if you want to use the kh variation. Okay. So, the one variation will be that you can simply write that my I can consider that kh variation, so variation of kh. So, kh here we have not talked about the kh variation. So, what will be the kh variation? Now, kh variation will be linear, then in that case that P will be kh into y. Okay, so that means that at any point that P stress is linearly varying with the deflection. Okay, so that is the linear variation, or I should write. So, no, this linear variation I will write later on. First, I am writing the kh, variation of kh. So, variation of kh can be in different types. So, this is the kh is equal to eta h, then z by d. So, that is one variation we have already used. So, this variation is linear. So, kh is varying linearly with depth. Okay, so, previous solution. So, this is the variation. So, another variation can be that kh is equal to eta h z to the power n by d. So, now if n is equal to 1, then this will be the linear variation, which is same as this one. But if n is greater than 1, then it will be not a linear variation, it will be a non-linear variation. Okay. Or for non-linear variation, you can write kh in different form, that is 1 by d k 0 plus k 1 z plus k 2 z square. Okay. So, these also you can write in different form. So, this is the different variation of the kh. It can be linear, it can be non-linear, depending upon your requirement. You can put them in the equation, because now it is so flexible that you can put the different variation at your in the equation, and you can apply this variation at different nodes, and you will get the your result by using the different variation or the variation you want. Okay, so then the Py relationship, that is the stress and the deflection relationship, or the Py variation, I should say, and P is the stress, Y is the deflection. So, the linear variation is that P is equal to kh into y. This is the linear variation. Then the non-linear variation also, that means P is equal to kh y to the power n, or P is equal to k z to the power m y to the power n. Okay, so, these here this k m n are the determined coefficient. So, this k m n are the coefficient, those can be determined experimentally. So, that means here not only you can give different variation of kh, but you can give the different variation of the Py. That means, whether you will put a linear variation, that means in previous expressions that k, that means here the stress strain behavior or the load settlement behavior is linear, but you can put non-linear variation also. Okay, because this is the first one is the linear variation, second are the non-linear variation. So, that means here that beams are not only resting on the linear spring, that means it can be resting on the non-linear spring also. That means you can incorporate the non-linearity in the load deformation behavior. You can put the non-linearity in the variation of the KH along the depth. So, this variation of the KH is along the depth. So, that we can incorporate in this equation and then we can solve it. Okay. And another thing is that as yes. So, as you know that your this that means KH value is not constant with the depth, it is varying for this granular type of soil. So, you can vary this KH, and if you want to make it uniform, because for the cohesive soil it is uniform, then you can make these things uniform also. Even this stress strain relationship or deformation and the load versus deformation or the stress versus deformation relationship also changes along the depth. Okay. So, deformation versus your load or the load versus deformation behavior, that also changes along the depth. So, that also you can incorporate here, because as I mentioned, for different node you can put different variation, and if you decide to know there will be different variation and different node, that also you can incorporate here. So, that means all this type of flexibility are there in this type of solution, where you can put a different variation of KH along depth, you can different variation of P and Y, you can put it linear, non-linear, or you can have a PY variation along